All right, this is the last one for gases, so let's get this taken care of so we can move on, right? So now real gases, where the ideal gas law fails. So if we rearrange the ideal gas law so that PV over RT equals N, right here, so if we put 1 mole of any gas in, so that means that pressure times volume divided by R times T has to equal 1 for an ideal gas. Now, in the real world, though, that doesn't happen. And so in the graphic here, you will see that real gases deviate from that relationship. So the horizontal line that you see in the middle is that value of 1. And if real gases don't follow that, well, then we got to understand why. And so here's the thing. As far as the pressures are, if the pressure is less than 10 atmospheres or so, they're close enough that we can keep using ideal gas law to approximate the volume or the temperature of a sample of gas. But if we get above 10 atmospheres of pressure, we get a kind of a weird set of deviations away from ideal gas law. And so as you can see here, the blue line is hydrogen. No, it's CO2, excuse me. The blue line is CO2, and so as we get pressure down maybe 150 atm, we get a decrease in, it falls below that line, and if we continue to increase the pressure, we get up to, looks like 600 atmospheres or so, 540 atmospheres or so, and we cross that ideal gas line point and it goes back up again. In fact, the only one of our gases on this graphic that doesn't go to the negative with this scenario is hydrogen, the orange line. And so the reason for that is, well, gases don't really behave ideally. Okay, so if we look and we talk about kinetic molecular theory, what we talk about with kinetic molecular theory is that gas particles don't have any volume and we can just not worry about it. And that's not the case. There really are volume particles. Particles have volume, and that volume really does have an impact on how gases behave in the real world. We also said, according to KMT, that particles don't attract one another. That gas particles are just inert little marbles that just bounce around inside a container, and they hit each other and they impact that energy back and forth again, but they don't do anything else. They don't stick together, they don't do that. They just kind of keep on bouncing around. In the real world, that's not the case. And there's a couple of reasons for that. We see that at high pressures, because the pressures are so high, the relative size of the container can get smaller. And if the relative size of the container gets smaller, then the percentage of that volume that the particles take up gets larger. And because that percentage of particle size matters at a smaller volume, we see that that contributes to our non-ideal gas behavior. We also have some particles that do, in fact, have attractions to one another. And those attractions cause particles to behave differently, and that we just have to take that into account. Now, what's interesting about that is there is a way that we can do that. And the way that we can do that is by using something called the van der Waals equation. And the van der Waals equation is an ideal gas law version that we can use when gases aren't going to behave ideally. Okay? So if I was, just doing a reference, a quick, easy calculation to get a guess idea, I can use ideal gas law. But if I'm working in an industry where it matters and I'm going to be under really high pressures or really high temperatures with a series of gases, and the pressure that I'm trying to calculate is important for the way that I'm building my structure, ideal gas law is not going to cut it. And so that's one of the reasons that we would use van der Waals equations. And what the van der Waals equations does is it adds corrective factors. And those corrective factors are something that we can look up. They've been studied, they've been determined. And one of the corrective factors, A, accounts for the attractive forces between the particles, and the other corrective value, B, is a measure of the volume that the particles actually take up. So let me show you what the equation is, and we're going to do one example problem just to show you. This equation does get fairly complex pretty quickly, and so we got to be careful with that too. So here we go. This is the van der Waals equation. So we have parentheses pressure plus n squared, that's moles, times A, that is one of our corrective factors, divided by volume squared. That's one of our terms, times volume minus number of moles times B, the other corrective factor, is going to equal number of moles times ideal gas law constant times T. Okay, so this is a much more complicated equation, but because it's a much more complicated equation, it gives us better information and it gives us more reasonable numbers instead of just a rough approximation. Okay, and again, B is a measure of the volume that the particles actually take up, and A is the measurement of the attractive forces between particles. Now, we can look up all these values. There are tables for them. They're available in most chemistry textbooks. They're the CRC. I would hazard to say you could probably find them online if you had to. So we can do this calculation with all kinds of gases and hopefully get some real value there. So we're going to do one example with this, and give me just a second. I'll be right back. All right, so here is our example. So if we have 10.0 moles of a gas confined to 22.4 liters at 0 degrees Celsius, we would expect that would have a pressure of 10 atmospheres using the ideal gas law. Now, let's find out if chlorine does that as well. So we're still going to use chlorine. We're still going to have a volume of 22.4 liters. Our temperature is right here. Really, that's 273.15 K. We still have a pressure of 10 atmospheres. So there's our pressure, and we still have an N of 10 moles. Okay, so here we go. Let's write our equation again. So it is pressure plus N squared A divided by V squared times V minus NB is going to equal nRT. Okay, here we go. I need P alone because we're trying to find a pressure. So we want to find the pressure of chlorine before we get there. So we need the A value and the B value for chlorine. Otherwise, we've got everything we need. I'll tell you that our A value for chlorine, where did I put it? V minus, okay, my A value is, goodness gracious, where'd you go? Okay, so my A value is 6.49 liters squared, atmospheres divided by moles squared. Okay, and my V, or my B correction, is 0.0562, and that is liters per mole. Okay, so now let's do some algebra. Okay, this is going to kind of be a pain. I'm sorry. Sometimes doing chemistry is actually more math than chemistry, but we want to get this P value alone. So the first thing I'm going to do is I'm going to divide the left side by V over NB, by V minus NB. I'm going to divide that. What I do to one, I do to the other. So V minus NB. So this is gone. So now I have P, come on marker, really, you're going to do this right now? Okay, P plus N squared A over V squared, hang on, I don't want that there, I want it like that, is going to equal nRT V minus NB. Okay, well, we can unparentheses this. So it's P plus this. So if we subtract N squared A over V squared, we do that to the other side, we get N squared A over V squared. Okay, so this is the equation that we're using. Here we go. Yeah, and so this canceled out. I forgot to erase that too. There you go. So P, and I'm going to rewrite it so it looks a little bit less dumb. P equals nRT over V minus NB minus N squared A over V squared. Yeah, that's a lot. I know. But like I said, it's more complicated, but It's okay. Take your time. You guys can do the pieces. I know you can. Okay. N, number of moles. So this is 10 moles. Actually, hang on. I'm going to slide over a little bit because I think I'm going to run out of space. So this is going to be 10.0 moles. So that's N. R is still 0.08206 liters, atmospheres, mole K. Temperature was 273.15 K. Okay, all of that is going to equal my volume, which we said was 22.4 liters minus 22.4 liters minus N times B. N is 10 moles, and B is 0.0562. 0.0562 liters per mole. Okay, so that's the first part of that. Minus N squared times A, so N squared is 10 moles. That's going to be squared, times my A value. So my A value is 6.49 liters squared atmospheres divided by moles squared. All of that mess gets divided by our V squared. Our V squared is 22.4 liters. So I'm going to write it down here so the arrow doesn't. 24.4 liters, or 22.4 liters squared. Okay, now let's start canceling units, all right? I'm going to start here. I have moles times liters per mole, so this is going to cancel away. Now my denominator is going to be in liters. I have, let's see, those are gone. We have liters up top, so now this liters goes away, so does that one. This moles goes away. This K goes away. So we have a pressure unit left behind there. Sweet. All right. This one is moles squared. I have moles squared in the denominator right here. So that's moles squared. That one will go away. And we're going to have liters squared here. There's liters squared here. So that unit goes away. So we have atmospheres and atmospheres, which is a pressure unit. So all right, cool. So the units actually work. So now we just have to do the math. So we do the math on it. 10 times 0.08206 times 273.15 divided by those two multiplied. Subtract that. So we got to do order of operations here as well. And then it's going to be that squared times that divided by that squared. Okay. All of that comes to fruition. You should have gotten 10.26 atmospheres out of this first term minus 1.29 atmospheres out of the second term. And so when I do that, I get 8.97 atmospheres total pressure inside that Cl2 container using those same conditions. So ideal gas law said that it would have been 10 atmospheres of pressure. Van der Waals equation says it was 8.97 atmospheres of pressure. Now, in the big picture, is that really going to change much for you guys as chemistry students? No, not really. But for you guys as chemical engineers down the road, 8.97 atmospheres of pressure versus 10 atmospheres of pressure, that is a critical design difference. If that's what you are doing for a living, you need to make sure that you understand the difference between ideal gas law and real gas law and how real gases actually behave. So with that, we have finished up all of our gas law material and we'll move on. So thanks for your time. Bye-bye.